You know, it really struck me when I first heard about this engineers simulating uh, millions of car crashes virtually, long before any real metal gets bent. It's kind of amazing how this hidden digital world has become so central to keeping us safe on the road. We often just assume cars are safe, right? That the engineers somehow, I don't know, just figured it all out over time. But there's this incredible amount of science and really painstaking analysis and some seriously cutting edge tech behind it all. And a huge chunk of that happens completely unseen in a digital space. So today, on the deep dive, we're going to pull back the curtain on that exact world. We're diving into how automotive engineers are, well, revolutionizing vehicle safety. Not with the old school physical smash ups, so those still happen, but mainly with these incredibly sophisticated virtual crash simulations. I mean, think about it. You've got global safety regulations, Euro NCAP over in Europe, the IHS, NHTSA here in the States. They're super strict. And traditionally, meeting those standards meant building lots of physical prototypes, expensive ones, and then, crashing them into walls again and again. It's hugely expensive, takes forever, and you burn through so many prototypes. But now the real game changer is virtual crash simulation. It slashes costs, boosts safety, and speeds up development like crazy. So our mission today is to unpack how two key pieces of software, CATIA for the design part and ANSYS LS-DYNA for the crash analysis, how they work together, almost like a digital dance, to make the cars you drive safer and actually more efficient too. So yeah, buckle up.
It really is a fascinating field.
Yeah.
Because it shows how computing power has gone from just, helping out to being absolutely fundamental to the whole engineering design process. The impact on safety and on innovation, it's pretty staggering.
Okay, let's unpack that a bit more. When you picture car design, maybe you think of engineers like on a factory floor, right? But
Yeah.
you're saying now so much of the critical safety work happens digitally. Why? Why this huge leap away from physical prototypes being the main thing?
Well, it wasn't just about convenience, it was almost a necessity, driven by the sheer complexity and, frankly, the enormous cost of the old ways. Think about the downsides.
Yeah.
Each physical crash test, that needs a fully built car, sometimes a specific version just for one test. And then that car is, well, completely destroyed, gone.
Right. Total loss.
Exactly. You've got the cost of materials, the manufacturing, the test facility itself, the engineer's time, and the time just spent building each one. Manufacturers used to need dozens, maybe even hundreds of these prototypes, each costing potentially millions.
Wow. Okay, so the pressure was definitely on to find a better way.
Definitely. Now, compare that to virtual simulation. The efficiency is just astounding. First off, cost efficiency. You need drastically fewer physical prototypes. Instead of smashing, say, 20 cars, you might only smash one or two at the very end for final checking, because you've already run thousands of tests virtually.
Okay, that makes sense. Fewer crashes means less cost.
And that leads straight to faster development cycles. You're not stuck waiting weeks or months for a new physical prototype to be built just to test one change. Weaknesses. You spot them and fix them in hours or days, right there in the digital design phase, not way down the line when fixing things gets exponentially more expensive and difficult.
So you catch problems much, much earlier.
Precisely. Which also directly impacts regulatory compliance. Engineers can tweak and refine the design virtually over and over until they're confident it'll meet those tough global standards, before they even think about building the first physical car.
So they know it should pass before they even try the real test.
That's the idea. And finally, there's design optimization. This is huge. You get the freedom to test countless different materials, different thicknesses for parts, various structural layouts, completely new ideas, all without any extra manufacturing cost. Each virtual test is just computing time, essentially. Not physical parts, not factory time.
So the core idea here is shifting from that sort of destructive, expensive trial and error to predictive, really precise digital engineering. Building safety into the cars like digital DNA before it even exists physically. But, I mean, it sounds almost too perfect. Are there still challenges or drawbacks? Is it truly a silver bullet for car safety design?
That's a really good question. And no, it's not quite a silver bullet. It's incredibly powerful, yes, but simulations are only as good as the data you feed them. You need super accurate input data, material properties, how strong the welds are, things like that.
Yeah.
And you still need highly skilled engineers to set up the simulations correctly and interpret the results.
Ah, okay. So the quality of the input is critical.
Absolutely. And extremely complex simulations can still take a significant amount of computing time. So while we massively reduce the number of physical tests, they aren't gone completely. They're still vital for that final validation, kind of a reality check. bridging any small gaps between the virtual model and the real physical car.
That makes perfect sense. It's a tool, a very powerful one, but not magic. So for you, the driver listening, what this all means is the car you drive has likely been tested and tweaked maybe thousands of times in every way imaginable, all before it even left the digital drawing board. It's kind of a shortcut to understanding those hidden layers of safety in your car. Knowing the crumple zones, the beams in the doors, even where the airbags are placed, they've been refined to this incredible degree before you even sit in it. It's actually pretty remarkable when you think about it that way.
Precisely. It's about embedding safety right into the core concept of the vehicle from the very, very beginning.
Okay, so if we're going to crash this virtual car, first we need to build it virtually, right? You can't just like throw a generic car shape at a digital wall. You need every detail, every bolt, every material. That's where CATIA comes in. You mentioned this CAD modeling tool. What exactly is its role in creating this digital safety blueprint?
Yeah, CATIA is essentially the digital architect's main tool set for automotive engineers. It's where the entire vehicle gets meticulously designed piece by piece in 3D. And for crash simulation setup, its capabilities are absolutely fundamental. You have to get this part right.
So what does that involve specifically?
Well, first, engineers create incredibly detailed 3D chassis models. And I mean detailed. It's not just a rough shape. It's the whole frame geometry, the exact curves of the body panels, every single important reinforcement beam, all mapped out in virtual space.
Every little bracket and connection point?
Everything that affects structural integrity. Then, and this is really critical, they assign material properties to all those different parts. It's not enough to just label something steel. You have to define what kind of steel, its specific yield strength, its ductility, how much it can stretch before breaking, its elastic limits. Same goes for aluminum, or advanced composites like carbon fiber, or plastics.
Because different materials behave totally differently on impact.
Totally differently. And those properties are key for the simulation to predict how the structure will actually behave when it hits something. CATIA's flexibility also allows for quick design variations. This is super useful. Engineers can compare, say, a design focused on being lightweight for fuel economy versus one using high-strength steel focused purely on occupant protection.
And they can just swap things out digitally?
Yep. Tweak a beam's thickness, change its material from steel to aluminum, maybe add a reinforcement, all with a few clicks. And they can immediately see the potential effects on weight and, crucially, structural integrity.
Wow, okay.
And finally, it handles complex assembly models. It's not just the car's shell or frame. CATIA lets engineers bring in all the interior parts that matter for safety too. Things like the seats, the dashboard structure, the bumpers, even the precise folded shape and location of airbags. Because how all those things interact during a crash is just as vital as the chassis performance itself.
Right, the whole system matters. Okay, so maybe an analogy helps here. Like, imagine building a complex Lego car, but you have like infinite types of bricks, right? And each brick has these super specific real-world properties, strength, weight, how it bends, and you could instantly swap out a whole section, maybe make it stronger or lighter, or even try a totally different design just by clicking around. I bet that's way less frustrating when my childhood Lego creations inevitably hit the floor and shattered. You had to start all over.
Yeah, that's actually a pretty good analogy. CATIA essentially lets you build that hyper-realistic digital twin, a canvas where safety is designed in very meticulously, pixel by pixel, long before any real metal gets cut or shaped.
A digital twin. I like that. Functionally identical, but endlessly changeable before you commit to manufacturing.
That's the core idea. Get it right digitally first.
Okay, so now we have this perfect virtual vehicle modeled in CATIA. Every beam, every panel, every material property defined. It's ready for its moment of truth, the virtual crash test. And this is where ANSYS LS-DYNA steps in, right? Taking that super detailed design and turning it into a dynamic impact analysis. This isn't just a visual smash-up. It sounds like some seriously complex physics simulation. What's LS-DYNA actually doing?
You're absolutely right. It's far from just a visual effect. ANSYS LS-DYNA is what we call a powerful explicit dynamics finite element analysis solver. It's specifically built for these kinds of highly nonlinear, very fast, transient events, like collisions.
Okay, hold on. Explicit dynamics, for those of us not deep in engineering, what does that mean in the context of a car crash?
Sure. Think of it as software that's brilliant at calculating things that happen very quickly and involve large deformations, like a car hitting a wall. Everything changes in fractions of a second. Materials bend, break, interact. LS-DYNA is designed to capture those instantaneous, highly dynamic forces and deformations really accurately.
Got it. Fast, violent events. So what's the first step when LS-DYNA gets the model from CATIA?
The first absolutely critical step is meshing. The complex, smooth CAD model from CATIA needs to be broken down into lots, thousands, sometimes millions, of small, manageable pieces or elements. Think of it like taking a smooth surface and covering it with a fine grid of tiny triangles or squares.
Okay, why do that?
Because it allows the software to perform calculations. It calculates stress, strain, and deformation at the corners or nodes of each tiny element and figures out how those forces travel through the whole structure during the impact. Without good meshing, the results, frankly, would be unreliable.
Right, you need those points to do the math. What's next?
Next, engineers define the boundary conditions. This is basically telling the simulation how the crash is going to happen. They set up the exact scenario. Is it a frontal crash at, say, 64 kilometers per hour into a fixed barrier? Is it a side impact from another vehicle or maybe hitting a pole? Or even a complex rollover scenario. They define what the car hits, the speed, the angle, all the specifics.
So you're recreating the official test standards virtually.
Exactly. Or exploring other what-if scenarios. Then comes simulating material behavior, and this is incredibly complex stuff. Materials don't just, snap, they bend, they stretch, they might tear, they deform permanently. LS-DYNA has sophisticated models for this. It accounts for something called strain rate sensitivity, meaning material might behave differently if you deform it slowly versus hitting it really fast like in a crash.
Ah, interesting. Steel might act differently at high speed.
Precisely. It also simulates plastic deformation where the material gets permanently bent out of shape and various failure modes like when and how a material might actually tear or fracture under extreme stress.
Okay, so it knows how the materials will really act. Then what?
Then the software analyzes the impact forces and energy absorption. This is where you see how well the safety features actually work. How effectively do the crumple zones, crush and absorb energy to keep it away from the passengers? How well do the seatbelts restrain the occupants? How do the airbags deploy timing, pressure, coverage to cushion people?
So it tracks everything, millisecond by millisecond.
In incredible detail. It tracks forces, accelerations, deformations, everything happening throughout the structure and to the occupants. Well, the virtual crash test dummies, over those critical milliseconds of the crash event.
And after the simulation runs, which I guess takes a while.
Oh yeah, it can take hours, sometimes even days on powerful computers for a really complex high-fidelity model. After it runs, engineers move to post-processing. This is where they review and make sense of all the data. They look at visual animations of the deformation, they analyze how much the structure intruded into the passenger cabin, and they check specific injury criteria for the virtual dummies using detailed, often color-coded, stress and strain maps.
So the colors showed danger zones.
Basically, yes.
Yeah.
These maps highlight areas of high stress, potential failure points, or excessive deformation. It shows exactly where a part might break, or bend too much, or where an occupant might be at higher risk. What's really fascinating and powerful is that LS-DYNA doesn't just show you if something broke. It shows you how it broke and why it broke. It gives engineers this unparalleled insight into occupant protection that you just couldn't get by, watching a physical crash test, even in slow motion. It's like having a microscope during a high-speed collision.
That level of detail is obviously incredibly powerful, but it must generate a ton of data. How do engineers actually sift through all that complex information efficiently? And, if LS-DYNA is that good, why bother with any physical tests anymore? Is it purely validation, or are there still things the virtual world just can't quite capture perfectly?
Both great points. On the data side, the post-processing tools are very sophisticated now. They allow engineers to visualize the results in really intuitive ways. Those color maps we mentioned, animations showing the deformation over time, graphs plotting forces or accelerations, they don't have to just stare at raw numbers.
Okay, so the tools help make sense of it all.
Definitely. And regarding physical tests, yes, they are still essential for that final validation. Because while the virtual models are incredibly accurate, they are still models, representations of reality. Sometimes unexpected real-world factors, maybe subtle variations in manufacturing, or a material behaving slightly differently under very specific, unique conditions can crop up. Physical tests confirm the virtual predictions. They act as that ultimate real-world stamp of approval before the car goes into production.
Got it. So LS-DYNA is like this amazing digital crystal ball showing the how and why of failure down to the smallest detail without breaking anything real. But the physical test is the final reality check. You mentioned this workflow, this cycle. Can you just quickly recap those steps? Because that integration seems key.
Absolutely. It really is a continuous loop focused on improvement. So step 1, Design the 3D model in CATIA, all the geometry, materials, everything. Step 2, export that model to ANSYS LS-DYNA, usually using standard file formats that both understand. Step 3, apply the meshing, break it into those finite elements, and assign the detailed material behavior models within the ANSYS environment. Get it ready for analysis.
Setting the stage.
Right. Step 4, define the specific crash scenario. Frontal, side, pole, rollover, whatever you need to test, including speed and angle.
Tell it how to crash.
Exactly. Then the big one, step 5, run the simulation. Let the software calculate all those forces, stresses, deformations, accelerations, injury risks.
Number crunching.
Yep. And finally, step 6, analyze the results. See what happened. Did anything fail? Was intrusion too high? Are injury metrics okay? And crucially, if needed, and it usually needed, initially redesign the weak areas. Then the loop starts again, back to TTAF for modifications based on the simulation results.
Design, test, refine, repeat. That sounds incredibly efficient compared to building prototype after prototype. But is this tech just for the big car companies? Or does it have wider uses?
Oh, that's a really important point. While automotive is definitely a primary driver and user, the principles and the software tools are used much more broadly. Obviously, in automotive engineering, it's about simulating chassis for safety, yes, but also for optimizing weight reduction, fuel efficiency, and general performance under load. But in general, mechanical engineering, students and professionals use these tools to study structural deformation under high-speed impacts for all sorts of things. Maybe designing protective cases for electronics or aerospace components that might face impacts, even things like designing better sporting equipment.
Huh, interesting. Like helmets?
Could be helmets, protective gear, yeah. Then you have material science. Researchers are heavily using simulation to test the performance of brand new materials. How do advanced composites stack up against traditional steel or aluminum in crash scenarios? They can rapidly assess if a new alloy, or maybe a new way of weaving carbon fiber, offers better energy absorption or strength without having to physically make and test samples for every single variation.
So it accelerates materials discovery, too.
Absolutely. And for wider research projects, this technology is vital. Think about developing lightweight, yet super strong and crash-resistant designs. This is hugely relevant for emerging types of vehicles, like those urban air mobility concepts, flying taxis, or maybe next-generation high-speed trains. They all need to be light, but incredibly safe.
Wow. So this isn't just about making your next SUV safer. It's actually shaping innovation across mechanical engineering, materials science. It's really empowering students and researchers in a lot of fields. Kind of reminds me of those old stories from the early days of crash testing. Didn't they use, like, actual fruit or something to simulate impacts before they had proper dummies? We've definitely come a long, long way from that.
We certainly have. It fosters this much deeper understanding of how materials and structures behave under extreme conditions, which is just invaluable across the board.
Okay, let's shift gears and look ahead. This technology, it's not standing still, right? It must be evolving, especially with all the massive changes happening in the car world. Electric vehicles becoming mainstream, autonomous driving features, totally new vehicle shapes maybe. What's next for virtual crash simulation?
Yeah, connecting this to the bigger picture, these simulation advancements are absolutely crucial for tackling a whole new set of safety challenges that come with these new technologies. One of the biggest areas right now is EV battery safety simulation. Electric vehicles, they have these large, very heavy, high-voltage lithium-ion battery packs, often built right into the floor structure.
Right, the skateboard platform.
Exactly. Protecting those batteries during a crash is absolutely critical, not just for the occupant's safety directly, but also to prevent something called thermal runaway.
That sounds bad. What is it?
It's essentially an uncontrolled self-heating process within a damaged battery cell that can spread and potentially lead to a fire. Very serious. So simulations are now intensely focused on designing structures that shield these packs effectively under all sorts of impact types.
Okay, so protecting the battery is a huge new focus. What else?
Then there's the rise of AI-powered crash prediction. We're starting to see machine learning models being developed that can analyze early design parameters and actually predict potential weak spots or suggest optimal design configurations before you even run the full detailed LS-DYNA simulations.
Whoa, like AI suggesting improvements up front.
Kind of. It could help guide engineers towards inherently safer designs much earlier in the process, potentially speeding things up even more. It's still developing, but the potential is there.
Fascinating. What about materials?
The push for lightweight materials isn't slowing down. If anything, it's accelerating, especially with EVs where weight saving is key for range. Simulation is vital here.
Mm.
Continued research and virtual testing of advanced materials like carbon fiber composites, new alloys, hybrid materials, it's essential. Simulation lets engineers understand their complex behaviors under impact, like anisotropic properties.
Meaning they're stronger in one direction than another.
Exactly. Like
Uh-huh.
wood grain, but more complex. These materials often behave differently depending on the direction of the force. Simulation helps model that, which is really hard and expensive to figure out just through physical testing for every new material idea.
Okay. And you mentioned digital twins earlier.
Yes. Digital twin technology is a really exciting frontier. This involves creating a direct link between real-world data and the virtual simulation models. You might take data from physical crash tests or even sensor data collected from vehicles driving on the road, how suspension is handling bumps, braking forces, maybe minor incidents, and feed that back to continuously update and refine the virtual model. This creates these highly accurate, constantly improving digital replicas of vehicles. They learn from reality, making future simulations even more precise.
Okay, that raises a pretty profound question, doesn't it? What happens when a car isn't just designed to be safe based on simulations before it's built, but it's potentially constantly learning and improving its own safety understanding after it's built through its digital twin, using real-world events to refine its virtual counterpart? The possibilities for truly proactive, evolving safety seem incredible. That line between the digital design and the physical reality just keeps getting blurrier. It's a remarkable idea, feeding real-world results right back into that design loop.
It really is a potential paradigm shift. The vehicle, in a sense, could become a kind of living, learning entity from a safety standpoint, constantly refining its own resilience based on collective experience.
And that seems like a perfect place to wrap up this deep dive. Today, we've peeled back the layers on the really intricate world of virtual crash simulation. We saw how the powerful combination of CATIA for creating that detailed digital blueprint and ANSYS LS-DYNA for the rigorous virtual crash analysis is fundamentally changing how our vehicles are engineered. This whole process empowers engineers to build cars that are significantly safer, often lighter, and more efficient too, all by drastically cutting down on the need for expensive, time-consuming physical prototypes and speeding up those critical design cycles. And ultimately, this digital revolution has a direct impact on your safety when you're out on the road. It ensures that the cars of today and tomorrow can meet both the performance we expect and those increasingly tough safety standards. It's like a silent guardian, constantly working behind the scenes in the digital realm. So here's a final thought to leave you with. As we accelerate into this era of self-driving technology, electric powertrains, and maybe completely new ways of designing vehicles, could these virtual crash simulations become so incredibly sophisticated, so accurate that physical crash tests as we've known them for decades eventually become, well, maybe just a final formality? Or perhaps even a relic of the past? What new frontiers in vehicle safety could that unlock for you? Something to ponder. Until next time on The Deep Dive.